Hey there, and welcome. Have you ever stopped to think about how some things grow, not just by adding a little bit at a time, but, well, by exploding? Think about it like a viral video that just doubles its views every single hour. Or maybe money in a savings account that keeps growing through compound interest. Well, today we're going to pull back the curtain on the mathematical pattern that makes all that explosive growth happen.
Okay, let's just dive right in. No messing around. Take a look at this sequence of numbers. 2, 4, 8, 16. See how it's not just growing, it's accelerating. I bet you can already spot the rule, right? Yep, each number is just double the one that came before it. We're multiplying by 2 every single step. And you know what? That simple little act of multiplying over and over again, that is the absolute key to everything we're going to talk about today.
So that multiplier, the one that keeps showing up again and again, that's kind of like the secret ingredient here. And of course, it has a special name. It's really the one thing that defines this whole pattern we're exploring.
And here it is, the official terminology. This kind of pattern is called a geometric sequence. And that multiplier, the one we keep talking about, that's called the common ratio. So from now on, whenever you hear geometric sequence, all I want you to think is it's just a list of numbers where you multiply by the same thing every time. Simple as that.
Okay, check out this example. We've got 1, then 5, then 25, then 125. The pattern here is, well, it's pretty obvious, isn't it? Each step is exactly 5 times bigger than the last one. So that number, 5, that's our common ratio. All right, so knowing the definition is one thing. But what happens when you're out there in the wild and you find a sequence of numbers? How can you be sure it's geometric? Well, it turns out there's a really simple test.
And here's the trick. It's super simple. If you multiply to go forward in the sequence, what do you think you do to go backward? You divide. So to find that common ratio, all you have to do is take any number in the list and divide it by the one that came right before it. If you keep getting the same answer every single time, boom, you've just proven it's a geometric sequence.
Let's try this out. Look at this sequence. 120, 60, 30, 15. Okay, let's do the test. What's 60 divided by 120? That's 1/2. All right, what about 30 divided by 60? Also 1/2. And 15 divided by 30? You guessed it, 1/2 again. See, the ratio is times always 1/2. So we know for sure this is a geometric sequence.
But what about when it's not geometric? Let's look at this one. 2, 6, 11, 17. Okay, let's test it. 6 divided by 2? That's 3. Easy enough. But what's 11 divided by 6? That's something like 1.83. The ratio changed right away. Because there's no common ratio, this is not a geometric sequence. It's all about that consistency.
All right, time for you to try one. Take a look at this sequence. 8, 24, 72, 216. So, what do you think? Is it geometric? Go ahead, do the division test real quick.
And the answer is yes, it totally is. 24 divided by 8 is 3, and 72 divided by 24, also 3. The common ratio is 3, all the way down. So, yep, it's a geometric sequence. Nice work if you got that one.
Okay, so we're getting pretty good at spotting these things. What's the next step? Well, how about we try to continue the pattern? Once you've got that common ratio, you basically have the keys to the kingdom. You can predict exactly what's coming next.
This is a perfect example. We've got 3, 6, 12, 24. You can see the common ratio is 2, right? So what's the next number? We just keep the pattern going. 24 times 2 is 48, and the one after that, 48 times 2, which is 96. You just keep multiplying by that ratio. So really, it all just boils down to a super simple 3-step process. Step 1, find that common ratio. Step 2, multiply the very last number you have by that ratio. And step 3, just keep doing step 2 over and over again for as many terms as you need.
And you know what's cool? This works even when the numbers get a little weird. Look at this one. 64, then -16, then 4, then -1. Wow. The common ratio here is actually a negative fraction, -1/4. But the logic is exactly the same. You just keep multiplying by -1/4, and the pattern will continue perfectly.
So we've been playing with the numbers, which is fun. But for me, the most interesting part is what happens when we try to see this pattern. Like if we were to draw a picture of it, what shape would it make? Any guesses?
Okay, let's actually do it. Let's visualize this. Imagine we take a sequence like 32, 16, 8, 4, 2, and we plot it on a graph. The first number is at position 1, the second at position 2, and so on. So we get these points, 132, 216, etc. And when you start plotting them, you notice something right away. They do not make a straight line. A totally different shape starts to appear.
And that shape? It's an exponential curve. That's the name for it. It's not straight at all. It's a curve that either shoots up or dives down faster and faster. This swooping shape, it's like the visual fingerprint of every single geometric sequence.
You know, the source material says it perfectly. The points appear to lie on an exponential curve. And that's really the big aha moment here. Every single one of these sequences, this pattern of just multiplying over and over, has this beautiful, elegant curve hiding inside it.
So let's do a quick recap of everything you can do now. First, you can spot a geometric sequence from a mile away just by testing for that common ratio. Second, you can continue the pattern, extending it as far as you want. And third, you know that if you ever graph one, you're going to see that awesome exponential curve.
And look, this isn't just some abstract math thing you find in a textbook. This pattern is everywhere. It's how money grows with compound interest. It's how populations can explode. It's even how a bouncing ball loses a little bit of its height with each bounce. So I'll leave you with this question. Now that you know what to look for, where do you see this kind of exponential growth or decay happening in the world all around you? Think about it.